Hi there, in a previous video I covered my futile attempts to make the membrane keyboard of the TTI 1905A multimeter working. The problem is the disintegrating keyboard cable riddled with cracks. It is part of the keyboard itself and can't be replaced separately. I contacted TTI and no, there are no spare keyboards available from them. I was told this was one of the first things they ran out of, which doesn't surprise me as this failure is a common problem of the otherwise excellent 1905A. In the previous video I fabricated an external keyboard box. It is bulky and inconvenient and not a permanent solution, but it allows me to explore what the 1905 with an intact keyboard can do. One of the most annoying things is that at power up the meter always starts in a 4.5 digit mode. Hence, at least for me, one of the most frequently used functions is to turn on the 5.5 digit mode. And using the secret ** button first and then pressing the 5.5 button, you can enter the 6.5 digit high resolution mode. As you saw earlier, this high res mode works for DC volts, but also for resistance, demonstrated by this 10K resistor, but not for currents. There, 5.5 digit is the best you can have. And measuring 1000 millivolts AC shows in AC mode 4.5 digits is all that's available. These limits are understandable since it makes no sense to show more digits than justified by the accuracy, which is generally in nearly all multimeters worse for current and AC modes because of the additional circuitry needed. Next, the NULL function, most often used for resistance, but it can be used for other modes as well. Here's a voltage of about 10 millivolts. If I press NULL, the display shows a 0 with an N on the right as a reminder that NULL is active. Pressing NULL again cancels the NULL function. Interestingly, this meter stores the NULL offset as the number shown on the display when NULL was pressed. As a consequence, if you change range, it now subtracts an offset with a decimal point at a different place of what is now measured, and the result is likely not what you would expect. But the meter warns you about that. In 6.5 digit mode, there's no space for showing the N, but otherwise the meter behaves the same way. And going back to 4 or 5.5 digit mode shows the N. The hold function works pretty much as you would expect. Instead of N, you see a H. In the 6.5 digit mode, you don't because there's no space. Other than with NULL, if I change the number of digits, hold is automatically cancelled. Changing range during hold gives a brief error warning, but the display stays on hold with exactly the same value, no change in the decimal point. So you should not do this because this frozen value is not 10 volts in the 20 volt range as you would think. It becomes obvious when I turn off hold. Let's try some of the programs. I start with decibels. If you enter it, it asks if you want to enter a value. Review shows the default. For dB volts, you need to enter the reference voltage, nominally 1 volts, or for dBm, the impedance in kilo ohms. You see how entering a number works. Let's stick with 1 volt and press enter. The meter asks if you want to run the program and I confirm with pressing run. The display changes to dB volts, which is 0. I can change the output of the generator to different values. I can, for example, lower the output of my function generator by -10 dB volts, and that is what the meter shows. Note the blinking decimal point. That shows that at least one program is running at the moment. A fast way of cancelling all running programs in one go is the 0 cancel button. The display returns to AC volts and the decimal point is not blinking anymore. If I run the dB function again, the program skips the reference input for convenience and goes immediately to ask for run. But if I want, I can look at it or change the reference by pressing review. To cancel just one specific program, if several are running at the same time, I need to select the program first and then press cancel. Another program is called AvLoHi. It shows, easy to guess, the average, the low and the high values. When you first start it, the program goes right into the run question. Letting it run a bit, indicated by the blinking decimal point, pressing AvLoHi again, and now we can use the recall button to see the average, the low value, and the high value. The blinking digits show that this is a recalled value, not a live measurement. In 5.5 digit or less mode, it would show a blinking R for recall instead. I can resume the program pressing the continue button and recall again for an update. Or press run clear to do a new run, clearing the previously collected data first. Or I could just press cancel, which stops the program but does not clear the data. As long as the power is not lost, I can still use recall to look at the values. The delta program calculates the deviation in percent from a nominal value. I'm using this for ohms in this example. I have to enter the nominal value and the preset happens to be 10.0, which is fine for testing several 10K resistors in the 20K range. Trying my best 0.005% reference resistor first. Okay, the meter tells me it's 0.0006%. My second test, a 0.01% part, and the meter decides it's 0.0023% off. And this is a 0.1% resistor, which is rated 0.033%. Just for fun, putting a 1K resistor in series with 10K, and the meter says this value is 10.04% higher than the reference. Cancelling the program reveals the actual resistance of 11.004K. The limits program compares any type of measurement to a lower and higher limit. I'm using it for resistors again. First, I have to enter the higher limit. I'm selecting 10.1K for high and 9.9K for low, using the same resistors as before. It obviously leaves the last 3 digits of the display to show a space and PA, which stands for pass. And the same for the second. And the 0.1% 10K also passes, of course. A 1K resistor, on the other hand, is triggering LO for low, and 11K triggers high. The logger allows storing up to 100 measurements. When entered, it wants to know the period. 3 modes are available. First, manual mode, which is selected by putting -0 as a period. In manual mode, the values are stored only when the store key is pressed, like so. There's a brief display that the value was stored and at what location, starting with the memory location 0, then 1, and so on. To see the stored values, select the logger and then recall. It briefly shows the storage location, number 4 in this case, which is the last I used. Pressing recall step increments the location, which, since number 4 was the last, means it wraps around to memory 0, and then 1, and so on. The blinking last digit means this is a recalled value, not a live measurement. In 5.5 or less digit mode, it shows the letter R here. I changed the display to 5.5 digits and rerun the logger, going directly to recall to see the previous measurements again. Values remain stored until the meter is powered off. The values are of course the same, but with 1 digit less. The meter can now show the blinking R in the last digit. A second way to use the logger is when the period is set to 0 without the minus. This means log automatically as fast as possible. This is the default period value after power up. The meter now logs basically every acquired value as fast as it can, and there is no time to show a running increment of the memory locations as before. It is important to remember to cancel this program when done, otherwise the memory keeps filling even when you are looking at the previous values. As before, you can see values starting with the last, then wrapping around to the first. Every time recall step is pressed, the location increments. But you can change the direction with the +- key. Now I'm going backwards. I finish by using run clear. This clears all memory locations and then starts another logging. I am deliberately not interfering and just let it run. Remember, there are just 100 memory locations. Sure enough, it doesn't take long before we get a periodic alert full. that memory has been filled and further measurements are not stored. The last way of using the logger is to enter a positive value for the period. This is the period between recordings in seconds. I put 5 seconds in here. After running the program, I see every 5 seconds a brief message telling me the current value has been logged and at which memory location. A rather unusual program is decpt, standing for decimal point. The idea is that the thing you are measuring uses a different scale, for example, by using a high voltage probe dividing the input by 1000, so the values you see are really hundreds of volts rather than millivolts. decpt allows you to shift the decimal point of the display anywhere you want or suppress it completely. Here I set it to be on the left after the last 2 digits. And now we have something that at least looks like hundreds of volts on the display. Until I cancel the program and it's back to millivolts. If decpt was strange, the AX+B allows even more manipulation of the displayed values. I use that 100 ohm rheostat on the right for this demonstration. When put to the 5 on its scale, it shows 54 ohms. Moving it to scale 8 shows 83.8 ohms and so on. Let's say we want the meter to display the scale value directly. In other words, instead of 54 at scale 5, I want to see 5, and instead of 84, I want to see 8. In real life, you would use this most commonly for sensors reporting some physical measurements like temperature or pressure. To do this, I use the AX+B program. The first entry I have to provide is the scaling factor, A. Since I want 54 to show as 5.4, the A has to be 0.1. The second entry is the offset B. Since I want the 5.4 to show as 5.0, I have to subtract 0.4. Hence, I need to enter minus 0.4 as B. Running the program, and there you go. Scale 8 on the rheostat is now shown as 7.96, scale 5 as 5.06, and so on. Obviously, this isn't easy to hit 5 exactly with that code rheostat, but you get the idea that with the AX+B program, it's possible to map the display to show different values as long as they can be derived using a scaling and offsetting operation. The last of the programs. Congratulations if you're still watching. Filter basically allows you to adjust how the meter can suppress noise, mainly by averaging multiple samples, yet respond rapidly to changes on the input. Filter has a value between 0 and 7, and it's all explained in more detail in the manual available online, which I'm not repeating here. I find that the 1905A does a pretty good job without having to use filter, and I had to construct a pretty horrible signal to make a difference visible. This is basically a roughly 6 volt DC signal with a pretty heavy random noise on top. With the default, the meter is suddenly a bit jumpy. Applying the filter value of 5, which is the maximum for noise suppression, does have an effect of calming the display and getting closer to the display of the BM869S. Turning filter off and the display is slightly more jumpy again. I mentioned you can run multiple programs simultaneously. There is a predefined sequence in which they are executed, which is shown in the manual. In this case, I have enabled NULL and the programs delta and logger. Pressing review by itself shows the program or programs that are running at the moment. It's 8 and 2. The numbers correspond to the keys, with 8 being delta and 2 the logger. NULL is kind of a program but doesn't count as such. Using my makeshift keyboard substitute, I have shown everything you can do with a 1905A if you had a fully functioning keyboard. In part 1 I mentioned briefly some options to make a proper replacement, but all of these involve quite some work. The question I posed was whether the functions the keyboard offers are worth the trouble. I made this table which lists the functions in the order I presented them, what key or keys they need, and a somewhat subjective rating of the function's usefulness. Given the accuracy of the hardware, being able to access 5.5-digit mode is pretty much a must-have. Compared to that, 6.5-digit mode is nice but only adds resolution, not accuracy, mainly useful for seeing slowly drifting values. Being able to null is very important, especially for resistance measurements. Hold has its special uses, but it's not that frequently needed. The same is true for the AvLoHi function. It comes in handy in some cases, but not that often. The other functions are really more nice to have rather than really important. The one exception is possibly the logger for people who have no other means of logging. Then again, having to wade manually through 100 measurements is no fun. DEC-PT and AX+B are clearly for special cases only, and you can achieve the same by using real measurements and applying conversions yourself, possibly in a spreadsheet. Lastly, while the 1905A does a good job without extra filtering, the filter function would be nice to have because it can help in very tricky measurement situations. When you look at this table, it is clear that with just 3 keys we can do the 2 top priority functions and one of the next lower priority ones too. So here's my solution to the question. I implement a 3-key mini keyboard and remove the temporary full-size keypad because with its dangling box at a flat ribbon cable, it is awkward to store, move and set up the meter. A look at my reverse engineered schematic on the keyboard connector from part 1, it is clear that to be able to detect the 5.5 and star button, I need column line number 4 and row lines number 10 and 11. To include null, I have to add column line number 3. In total, I need 3 buttons and 4 wires. Yes, with these 4 wires I could also detect recall, but there is no point in wasting a key for that, since I would not be able to run any program that had anything to recall. This is the wiring I used, but feel free to do it differently. The 3 buttons are on a replacement blanking plate at the rear because that was convenient without having to destroy anything on the 1905A. The wires end up in what is commonly called DuPont female connectors, allowing them to be plugged onto the pins of the keyboard connector on the top PCB. My rather crude implementation, these are the 3 push buttons. And the same from the rear before the wires with the DuPont connectors are added. Once the wires are added, it looks like this. A view of the whole contraption. The idea is that it can be swapped relatively easy with a full-size external keyboard in case I really need one of the other programs. The new blanking plate with mini keyboard installed. And the DuPont connectors inserted. Compared with a full-size external keypad, the installed mini keyboard is very compact but can be easily swapped. It looks quite neat from the rear and I find it very easy to operate with a bit of practice. Switch to 5.5-digit mode. Null. Switch to 6.5-digit mode. I plan to put it on the bench when I need an additional meter that is easy to read in videos. The O1 and the back is often too far away for the camera, so you will probably see the 1905A more often in the future. If you like my videos, don't forget to subscribe. There are more repairs and reviews coming up, and it would be great if you decide becoming a Patreon. That would really help this channel. As Patreon, you always get early access to videos, a blog and other exclusive content. Thanks for watching.